Okay, so now let's take a look at class example program unit B3 page 4. Okay, this is a pipe flow, and then this is a special device called the flow rate measurement device. We are going to cover flow rate measurement device later, so this is just a sneak preview of what's going to come later. So let's take a look at it. Okay, so this is a flow rate measuring device. In fact, this section is called flow rate measurement device, which is a very simple device. In fact, you are going to just reduce the cross section of the pipe just temporarily. That's it. That's all it does. So this is called flow rate measurement device. It is installed in a horizontal pipe through which water is flowing. Okay. A U-tube manometer is connected to the pipe through the pressure tabs right here, located 3 inches on either side of the device. The gauge fluid of that U-tube has a specific weight of 112 pounds per cubic foot. Determine the differential reading of the manometer corresponding to a pressure drop between the taps is 0.5 psi. Okay. So this is again the same picture which I copied from the program statement. Like I said, this section is flow rate measurement device. It does really nothing, just reduce the cross section. What happens if you reduce the cross section? Incoming flow is going to be accelerated. The reason why it is accelerated is because cross section is reduced. As a result, you have accelerated flow. Okay. So flow is going through this in a smaller cross section, then velocity goes up. So acceleration is involved. So obviously, if you compare cross section 1, cross section 2, where the pressure tabs are located, right here the velocity is higher than that. If the velocity is higher than that, pressure needs to be dropping. This is called Bernoulli's equation. We're going to cover that later. But because of this flow rate measurement, which is reduced cross section, this P2 is lower pressure. P1 is higher pressure. The reason is velocity is higher and velocity is lower. You have to take a balance between velocity and pressure. Okay? So you are going to purposefully create the pressure difference by changing the cross section. This is called flow rate measurement device. So let's say delta P. Delta P is, of course, P1 minus P2. You are going to make a lower pressure P2. If this is 0.5 pound per inch, psi, pound per square inch, this is a given condition. Okay. By the way, the figure says Q. This Q is called volume flow rate. We are going to, of course, cover that later. In this case, unit must be how much volume is flowing per unit time. So this is cubic foot per second usually. That's the standard unit of volume flow rate. So the purpose of this device is to determine this. You can determine this by using simple device, something like this, combined with U-tube manometer. So U-tube manometer comes into play. So how? That's the important question. So Suppose this pipe is a horizontal pipe. Then somewhere on the pipe you're going to attach a wall mount U-tube manometer. So let's say you have U-tube manometer attached to the pipe maybe. Okay. So let's say this is a U-tube manometer panel. Located here. Somewhere along the pipe, right next to the pipe, you're going to attach this panel, which has a U-tube. U-tube is nothing but just a U-shaped tube. So let's call this a differential U-tube panel. So obviously, differential U-tube panel is going to be filled with some kind of gauge fluid. So what I'm going to do, I'm going to connect up, maybe using small cross-section diameter tube, plastic tube, something called Taiwan tube. You're going to use the tube connected between this pressure tab connected to the left leg of this U-tube. So let me do that. So I'm going to pick up maybe Taiwan tube. So connect up that tube between this pressure tab to a left leg of this U-tube. Okay? If you do that, obviously, this tube is going to be filled with water. Water is flowing inside. Now, within this tube, water is not flowing, but because it's connected to the pipe, you are going to, naturally speaking, introduce water to this tube and then U-tube also. Okay. Then this U-tube is filled up with a gauge fluid. This is a gauge fluid. Maybe something like that. Now the program says this gauge fluid comes with specific weight given, which is 112 pounds per cubic foot. So this is a gauge fluid specific weight. Okay. Now, right hand side of this leg is of course connected to this pressure tabs P2. So you're going to again use the Taiwan tube. Connect up this pressure tab to here. Okay? Now obviously, because this is a water flowing inside, so naturally you are going to introduce water into the tube also. So this tube is filled up with water up until it's going to meet with this gauge fluid. Okay? Now obviously, pressure P1 is going to be transferred to this left leg. So pressure here is P1, essentially the exact same pressure. Right here, of course, pressure is P2, transferred to here. So essentially this pressure tab P2 transfer the pressure to here. So pressure here is P1, and pressure here is P2. Obviously, pressure P2 is lower pressure, pressure P1 is higher pressure. So higher pressure fluid pushes gauge fluid and create the difference between left leg and right leg. Right? Creating the difference between left leg and right leg. Of course, this is a higher pressure side. This is lower pressure side. So this H is called differential gauge U-tube manometer reading. Reading of manometer. Okay, that's H. So the program is asking you, suppose if the delta P, pressure difference between P1, P2 is 0.5 psi, what is this H? That's the problem is asking. So how do we handle that? Well, first of all, this is something we really don't know. You can use a very long YouTube or very short YouTube, either way is fine. So this is a variable. So let's call this H1. So can we use any differential YouTube panel? Yeah, sure, of course. The only thing that matters is this H, not H1. But H1 is unknown, so let me just put H1 here. Okay. So the strategy is very simple. Of course, you know pressure is P1 here, pressure P2 here, and you know the delta P, P1 minus P2 also. So in that case, what is H? I guess the strategy is you start from P1, go all the way to P2, then squeeze out manometer equation. Or alternatively, you can start from P2, go all the way to P1, squeeze out the same exact equation. Okay, manometer equation. So let's do that. Okay. So, manometer equation. So I'm going to start from P1, okay, P1. Pressure here is P1, yes, sure. So let's start from here, pressure P1, which is transferred from the pressure tab here. You're going to go down, 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 and down to here, right here. This is the boundary between water and gauge fluid, right here. What is the pressure here relative to that? Well, is it higher pressure? Yes, because it's deeper. So how much higher? Gamma times H. H is this much. Gamma is water. So P1 plus gamma water times H1 plus H. This is exactly the pressure right here. Okay. Then you are going to go down more and then go here, then go back up here. So you are going to reach here. This is exactly the same pressure from here because it's in the same depths and same gauge fluid. So pressure here are the same, this way. Okay. So we are going to start from here, go to right here. What is the pressure here? Pressure here is whatever the pressure here minus, because it's go shallower, it's going to be lower pressure, minus gamma times this much H, right? Minus gamma of what? Gauge fluid. Multiplied by H. Okay? So this is the pressure pressure right here. That's right. So if you go a little bit more shallower right here, the pressure here is whatever the pressure here minus again gamma of water times H1. So this is the pressure right here, which is equal to P2. Yeah? So now I squeezed out manometer equation. Okay. So this is the manometer equation of this particular differential YouTube panel. Now, I guess you're afraid of what is H1. H1 could be any value because if you use a long tube, I guess H1 is big value. If you use a shorter tube, H1 is smaller value. So what is H1? Well, do not worry about that because if you take a close look at this equation, this and that cancels out from the equation. This subtract that one, but it's gone. So H1 doesn't matter. Oh, it's a good news. So let's simplify this equation. P1 plus, this is gone, gamma water times H minus gamma GFH is equal to P2. Okay? Well, we do know P1 minus P2. P1 minus P2, we do know this is 0.5 pounds per inch squared, which is equal to gamma GF times H minus gamma water times H, which is equal to H times gamma GF gauge fluid minus gamma water. So let's solve for H. What is H? H is equal to P1 minus P2 divided by gamma gauge fluid minus gamma water. Okay? We do know this is a 0.5 pounds per inch square. Let's convert it to pound per square foot. 12 inch over 1 feet square. Gamma gauge fluid is given 112 pounds per cubic foot minus water is 62.4 pounds per cubic foot. From here, H can be found 1.452 feet. So this is gauge reading of this differential U-tube manometer panel attached to measure this flow rate. So this flow rate can be determined. Usually you read off this H. This is going to actually determine how much pressure drop happened. If you determine how much pressure drop happened, it is going to determine flow rate. Okay? So we are going to discover this later after we introduce fluid dynamics, which involves Bernoulli's equation. But this is a sneak preview of what's going to come later. But I guess the important thing is you need to understand this is one of the good example usage of this differential U-tube manometer. One thing quite important here is differential U-tube manometer give you only one thing and one thing only, which is pressure difference between two pressure sources. This one can never determine exactly what is the P1 and exactly what is the P2. You can never determine such a thing. You can only determine pressure difference between two pressure sources. Now, in this particular purpose, that is good enough information to determine flow rate. We're going to find out later, okay? All right, that's it.